Welcome to today's lecture. This is analysis of three-way spool and flapper nozzle valves. This means that we shall consider three-way spool valve as well as three-way flapper nozzle valves. In last lectures, we have already learned about the four-way critical center valves. We have learned general design analysis of four-way valves, which is mostly applicable for servo valves. Now, the figure 10.361, this is figure 1, it shows the three-way spool valve, and this must be used with an unequal area piston to provide directional reversal. Now, what is three-way valve? We know that what is four-way valve, but four-way valve normally which are used for the motion control, that is we control the velocity, we control the position, we control also pressure there. In that case, normally the direction reversal are not frequent, or in other words, although directional reversal is done, the scope is there because it is a four-way valve, but it is usually connected to rotary actuators, and normally we do not go for reversal frequently. On the other hand, if we would like to go for a reversal, in that case three-way with the load cylinder, this arrangement is the best. Now, again this valve may be critical center or maybe a open center. Closed center valve means overlap valves are not desired because of the longer bandwidth at the middle. However, critical center valves are mostly preferred, although in true sense it is very difficult to maintain that condition, that critical center valve positions. Usually it requires frequent null adjustment. However, we shall discuss about that. We will look into the critical center three-way valve. Now, how it is working? If we look into this is the supply. Now, once instead of four-way valve, in case of three valve, supply is one to the valve one end and other end directly to the rod end side of the pistons. So, if we keep this is closed, then this will simply move upward directions. Now, let us consider if we keep it open, then in that case what will happen, the flow is going like this and the flow is also coming in this way, and if you think of the regenerative principle, and you will find that this will move in these directions, and as well as some flow is going out. This is for the control purpose. This is the in servo valve it always happens. Now, the rod and head side, we call this is head side and this is rod side. Okay. Now, if we look into this area is designated by AH and this area is designated by AR. Now, the rod and head side areas of the piston should be such that a steady state control pressure PCO is the control pressure of about half of the system pressure PS. Now, this PCO or simply PC, we need half of that for the better control. This means that we can express this control pressure is equal to PS, that is the system pressure by 2, that is desired. Now, for that what we would do, ideally it happens at area ratio half. What does it mean? That the head area of piston AH is double the rod end area AR. That means, here the AR is the area, is the annulus area. The head area means the full area. So, full area should be double of that annular area. That can be done, there is no difficult to do such things, but you should not confuse here that this does not mean the area the diameter of the rod is half of the piston area. It is not, the area is half, you have to keep in mind. So, usually you will find that you will find that this is also looking very thick, because this more than half of that I mean this diameter is more than half of the piston area. Anyway, this area ratio is maintained half ideally, or in other words the rod area is half of the cylinder area. This is just we can express in the formula like this, A is equal to 2 AR. These valves are made critical center for better response in servo control. Do you understand my point? I told that maintaining the critical center is difficult. This means that to make such valve critical center, both this groove, dimension of the groove, not only the width of the groove, but also the distance between these two grooves should match with the distance of the spool. And in fact, I would say matching these two dimensions in two different components is difficult, and it is normally in practice, if it is used for spool the servo control valve, in that case the spool and this is called sleeve. Actually, you will find in a body there is a separate sleeve is used for this outer member. In that case, these are made match parts. That means, say 10 set of spool and 10 set of outer members are taken together, and then each and every spool which is matched with the outer member, and then it is examined that really how much critical center it is. Best pair is taken for one valve, then perhaps next one. In that way, it may happen in a 10 sets of these two components, these pairs, 5 components may be rejected also. This is one thing. Second thing, when it is in under operations, then this adjustment with because this is driven by some actuator, this might be electrical solenoid. Now, adjustment with these solenoid positions and these spool positions, because the solenoid is not directly coupled, it will be directly coupled, but not a single component. the solenoid spool and this spool is not directly, not an integral part, they are just connected. So, sometimes this it deviates from these critical center positions, and that can be adjusted of course. Now, it is found that critical, because as I told, this is for reversal operations, that means it is some operations it is doing forward and backward. So, if there is if it is a overlap valve, then there will be difficult for position controlling or maybe this reversal time controlling. So, in that way critical center valve is better. Now, for that critical center valve, if you recall our earlier analysis, general analysis for this spool valve, then this can be written as the load flow can be written in the form of coefficient of discharge into A1 is the area of this orifice, and then 2 divided by this is the density of the oil, and then P1 minus P2. Here is the P2 and here is the P1. Remember, P2 is not equal to P0, P2 is the pressure here and this P1 is the pressure here. So, we can further write this equation that CD into W x V, x V is the the spool stroke, it is called stroke, the stroke A is x V. Now, W is, what is W? W is the peripheral diameter, periphery of the this, you can say this spool length, okay. This diameter into 2 pi, pi into this diameter will give W. Now, this means that this is, we are considering the rectangular port. Now, W is written as you, if you remember in general terms, sometimes instead of this continuous, this groove is continuous, instead of this continuous groove some rectangular holes are provided. If these this is of with rectangular holes, say 4, 5, 6 holes over the periphery, and that are usually equispaced. In that case also we can use this formula is equal to W, because that W in that case width of that each groove, each hole through the sleeves plus the number of such grooves. Anyway, this into the stroke length will give the total area open there, that is the orifice area, and so this is the equation we can write for the load flow. But when this is in the opposite direction, that means it is moving in the from downward directions, in that case this equation simply written as, we will consider the A2, and this is again we will find that it is in the opposite directions, and in that case only there will be the control pressure. That means, we are getting only control pressure over there. Okay. Now, we can plot that what equations we have written there, we can plot to study such a valve, performance of a valve. Better to plot such graph, and then we can understand that how it is performing. Now, it is same as in case of 4-way valve, except the change in abscissa scale. If you remember in what we have already studied the 4-way valve, in that case you will find in this axis P c by P s is equal to 0 here, and then it is varying in these directions negative and varying in these directions positive. That is for the from left hand side to the right hand side of this spool. In that case, we simply use this value in this abscissa. Now, here this is written in the dimensionless form, this is also in the dimensionless form, and we can observe these are the for different x b by x maximum. Okay. So, this ratio. So, all are in dimensionless form, and what we find, we should call this is the null positions. Okay. This is the null position. Now, at null q l is equal to 0, x b is equal also 0. No, here it is the x b is 0 is here, not that. This is in the 4-way valve, you will find this is the 0 position, whereas this is the 0 position for flow and as well as for the no, we have considered x b is equal to 0, that means this is the 0. So, this might be the curve, okay, at null positions. Now, there what we find, the control pressure P c is P s by 2, because we have taken the area ratio 2. So, at that condition P s by P c by P s is equal to 2, that means P c by P s is equal to 0.5, this means here. Okay. What we consider that Q L is equal to 0 and our control pressure is here at null position. Therefore, the valve coefficients at null positions of 3-way critical center spool valve can be written as from this. If you have attended the earlier classes, then you can find that Q L by del Q L by del x b, not theta L, this is del Q L. Okay. This is del Q, Q L by T. So, this is flow gain, that means how much gain will be there at null positions. This depends on that critical center or open center, and this ultimately can be written in this form. Next, we will look into the flow pressure coefficient. The flow pressure coefficient is written in this form. This is W, this also will be W, not omega. Okay. Now, the pressure sensitivity can be written in this form. Now, what we find that at null positions, due to looking into this curve, this will be 0, whereas the pressure sensitivity, which is actually this divided by this, that will become infinity, because this will have some value, whereas this will become infinity, which means pressure sensitivity at the null positions is infinity, means highly sensitive at the null position. Now, the flow gain is same. If you look into the 4-way valve flow gain, what we will find in this this 3-way valve is also flow gain is same, but pressure sensitivity is half that of 4-way critical center valve. This is from the equations. You have to compare the equations of those I have not shown here and the equations of 3-way valve. Therefore, the error to overcome loads will be more. Now, this we should understand that as the sensitivity is half of the 4-way critical valve, then the error will be more in case of 3-way valve. This means that again although the three-way valve is simpler in construction and it is very good for using selecting such valve in case of the reversal operations, that is for the mostly for the linear actuator, but what is there, the error will be more. That means, to rectify such error we need much stronger, better controller than the four-way valve. It also can be shown that the dynamic load errors are almost double, this due to this factor that limits the application of three-way servo valve. So, three-way servo valve you will find normally for the of course, I would say the machine tools and at many places these are used, but if we look into the time response, that means we need very quick actions. Suppose we are trying to position control very accurately and with almost no time, real time control. In that case, possibly we have to go for four-way valve, even if there are frequent reversal operations. Now, hydromechanical servos where greater errors are tolerable, the source positioning is mechanical and quite steep compared with the force loads imposed by the spool. For this reason, in case of such a system, three-way valve, the force equation describing spool motion is usually important and flow forces are not of interest. Usually, what we have seen that flow force has significant roles on the controlling of the spool in servo mechanism. Now, in that case, the argument is that as these are we are tolerating the errors and the source positioning is mechanical quite steep compared with the force loads. So, in that case we can go for three-way valve where the flow forces not that significant. Now, this is I have given the idea of three-way spool valve. Now, similarly, there are three-way flapper nozzle valve also. In flapper nozzle valve, we will see some advantage over the spool valve. First of all, it is less expensive, but mostly allowing higher leakage losses. Such valves are of low cost and less sensitive to dirt. This means that usually such orifice and you will find this flapper is moving, thereby this flapper area is being controlled, the dirt can easily go out. So, therefore, it is better than the three-way spool valve. However, always there will be leakage loss and that we should take care of. And obviously, the cost is because making of a spool will be more expensive than such flapper valve. Flapper driven by torque motor, this is usually you will find that a torque motor will be used there. What is torque motor? We know this motor principles. In that case, armature is such that with this armature it will generate some torque with the current. If we increase the current, then the more torque will be there. If we decrease the current, so there will be less torque. This is very common in the pilot stage of two flow control valve including servo valves. Now, if we look into the four-way servo control valve, you will find in the first stage there is two stage actually, because to drive the main spool we need much force, and sometimes what happens that there is a first stage valve through which the flow hydraulic oil goes to control the main spool. In that case, you will find this first stage usually made of flapper nozzle, but here I would like to mention, we will see that flapper nozzle is normally it is by double flapper. That means, on the other side also there will be such nozzle and flow is coming this way and from the other way, but this is what I have shown here. This is a single one, and we will, our basic analysis will be done only on the single one. Here also we have taken this cylinder with the same 1:2 ratio. Okay. The pressure flow curves have better linearity. Also, performance of these devices are quite predictable and dependable. Now, we shall consider the analysis of a single jet flapper valve. It is also called sometimes the three-way flapper valve. Okay. Because of this principle, the same we have seen, the same principle is used for the spool valve also. Now, the flow through a fixed orifice of area A0 in the upstream is modulated by moving the flapper to generate a desired control pressure P c. Now, here we will find that a fixed orifice A0 is provided. Now, flow is going through this. Now, this flow can further be controlled by moving this flapper. If we move this one, this will be closed, you will find that pressure will increase. Then due to this increase in pressure here the system pressure is remains same, there will be less amount of flow and this will be controlled. Whereas, in this direction there is no orifice. So, upstream means this we are calling the upstream flow. The curtain area is more important than the flapper nozzle orifice area. Now, this what is called curtain area? Now, this we would call, this is the nozzle area, and this area which is closing this end, this is called curtain area. Okay. So, this we have to know, one is called curtain area and another is called simply orifice area. Orifice area is this one, and curtain area is what I would say, that if I consider the this periphery over here into this depth, say this is initially x f o, this height into the periphery, that means pi into diameter here into this, that area is important than this orifice area. The working range of the control pressure is estimated by obtaining the block load characteristics. Expression of mathematical model are shown in next slides, and also we will look into this block load characteristics. Now, from the flow equations, what we know that Q1 will be Q2 plus load flow. That means, if we consider that this flow is Q1, then that must be equal to one load is going this way and another load is coming, another flow, sorry, the flow is being divided into a part is for the moving the load, a part from the just exhaust. Now, just controlling this one, we can control this flow also. So, speed control is also done by controlling this flapper. Flows are expressed following the orifice equations as follows. Now, the orifice equation is same, only thing in this case what we consider that A0 is the area, this is pi by 4 do, do is the diameter here. Okay. Now, this is the system pressure and this is the control pressure over here. So, this is the flow Q 1 total flow. No, D 0 is the diameter of this orifice, sorry, A 0 is the orifice here. So, we are writing the equations for this orifice, okay, which is simply, this is obviously we have considered a circular hole and normally it will be circular hole. There is no reason making of other shapes, neither rectangular nor elliptical, or so simply a drill hole you can consider. Now, Q 2, this flow is equal to A f area of, we should call this is the curtain area, and that becomes pi d n x f 0 minus x f, that is the curtain height, and C d f. Okay, the d n diameter is actually this diameter. This is maybe drawn in a wide way. D n is the diameter here, not this diameter, diameter of this orifice. So, d n. So, pi d n, this periphery, into the current curtain height will give us the orifice area here. So, Q 2 is expressed in this way, and here the P c is the pressure in the upstream, and in the downstream is the exhaust pressure, which is normally 0. That is why this is here we find 2 pressure turn, here only 1 single pressure turn. Okay. Now, x f 0 is the initial gap between the flapper surface and the nozzle when the flapper is in equilibrium. Now, look at that, we should take care of the direction of S f. X f. X f is the movement of the flapper which is positive in the upward directions. Okay. So, this means when it is moving in the upward directions, this curtain height is being reduced, because this is positive and here we have minus sign. But suppose it is moving in the opposite direction, do not forget to put x f itself is a minus. So, total curtain height will increase and total area will also increase. X f is the flapper displacement which is positive towards the nozzle. Essentially, when there is no load, there is no load flow, that means it is no load flow, then Q 1 is equal to Q 2, or in other words, if there is this is not moving, that means we want that it should not move, but still this is open, then whole the oil coming in, that should go out. In that condition, Q 1 is equal to Q 2, and P c by P s, if we write in that way, this will become this will be expressed in this form. The plot of above equation, that is the block load characteristic, it is called block load characteristics. This can be presented in this form. Okay. So, if this is the, this ratio is varying from 0 to 2.8. Now, how it can be 0? The A f itself 0, this area is equal to 0. How? This means that this is completely closed. That means x f in positive direction is equal to x f 0. In that conditions, what we will find, that P c is equal to P s. Okay, this is 1. Now, if we this extreme case what we have considered 2.8, that in that case, of course, this is the ratio. Remember, see here, to make this is 0, we can consider AF itself 0, but this ratio, when this has some value, then this ratio depends on the coefficient of discharge, area, etc. However, what we find, this is of course for a particular valve, what we find at 2.8 of this ratio, that P c by P s is 0.1 only. That means control pressure is 10 times less than the system pressure. Okay. So, this diagram is useful for to find out the operating conditions. Now, looking into the graph, it is apparent that P c by P s is equal to 0.6 is a good value for stability point of view. Now, why we say this value is from stability point of view? This is because of the reasons that if we move in these directions, then definitely we will find that control pressure is much lower than the system pressure, and in that conditions we do not have much control over this load. So, what we find that possibly if we be here, then this is of course, this is simply a just a comment, maybe this was found by the analysis that at that conditions the operation will be the best. Whereas, if we enter in this zone, say this is 0.6, if this is 0.8, perhaps this is 0.6 or this is 0.4, this must be 0.6, P c s is equal to 0.6 is this one, here it is 0.8. This is considered as a stable conditions, stability point of view. If it is in this side, what you will find that controllability will be difficult because it needs more accuracy, whereas in that case controllability will be difficult due to the fact that the control pressure is too low. Considering this as a criteria for design, the orifice ratio at the null point is derived as now this value we would like to put 1 because this pressure we want half, P c by P s is half. So, that means this we would like to put 1. So, this ultimately derived into in this form, and then it can be shown that it is good for it is a good objective for both 3-way and 4-way. 4-way means double jet. Remember, when there is another nozzle in the opposite directions which we call the double jet, this will be the 4-way flapper valves. This criteria also depicts that the system with the piston and 3-way valve needs the working piston of area ratio 1:2 for best performance and optimum drift. Now, this about this drift we should go to the to know more about this drift, we can consult the reference to which I will show later. But what is drift? Drift means that while we are using such 3-way valves, then we are moving the load both in plus minus directions. So, this means that it is operating something, and in most of the cases you may find this is operating another spool. Now, what is drift? You will find that when this is at the central positions, this spool, this piston cylinder what we have called, but this is basically controlling a spool that should be in such a position that that spool is also in the null positions. But due to the leakage and error, what it happens when this is in the mid positions, this may be what it is controlling, that is not in the null positions. So, this null position and that null positions may not match. So, that is called drift. Now, there is also technique that we can control the drift also. Okay. But this is important, however, we are not analyzing the drift. This, to know about this drift, we should consult these references. The equation for pressure flow curves can be derived by equation 8 and substituting equation 9 and into 10, and then these equations become like this. So, this is for the pressure flow curve, we derived these equations. You just substitute this and you can arrived into these equations. Now, similarly, substituting 12 and 13, we get these equations. Okay. Now, we can perhaps if we look into this equation, then this is plotted here in this curve, and this plot of pressure flow characteristics is finally expressed in 14 and this is presented here. Now, if we look into this, in this case also this is same as the spool valve. So, abscissa is same as, it is different from the 4-way valve, but here only we have consider only one side of this curve. In that case, obviously, this flow is this is 0 because the load flow can take in both the directions, and what we find that x f by x f 0 is here. So, this is basically the null positions. No, sorry, this is coming over here, this is the null positions, whereas for the movement of x f in both the directions, we get different curve. Okay. So, from there we can find out the valve coefficients. Now, if we differentiate 14 and evaluate at x f is equal to q L is equal to 0, that is for the null positions, and P c by P s is equal to 2, sorry, P c by P s is equal to 1 by 2, then we get the valve coefficient at null positions, and these are we can find we can express in this form. And null flow pressure coefficients is expressed by this, as well the pressure sensitivity is expressed by these equations. Now, this is important to know the null for each and every valve for 3-way, 4-way. So, null coefficients are important to understand how better is the valve in performance. The leakage or center flow at null is given by these equations. Now, here it is important, although it is a center sorry, this is a critical center valve, but still there will be some flow, some leakage flow. If you we have earlier discussed about the central flow. The central flow is important for a valve because that affects the flow gain. Okay. But this leakage can be expressed in this form. Obviously, in case of flapper nozzle there will be leakage, because we should not say the critical center flapper nozzle valve, because these two nozzles by no means will sit on this flapper, because there will be some gap. This means that there will be leakage. So, knowing this central flow is important for this flapper valve. Now, the striking force by the flow from the nozzle can be derived as in this form. We shall also discuss in the next lecture. Now, what is striking force? The striking force means this when the flow is coming on, then this is striking on this flapper, which is ultimately required to estimate how much torque is required. Okay. So, this F1 is estimated by this formula. With very small gap, if we make this gap is very small, that is in the null positions, or maybe in the even in the operations while we are moving this XF in these directions, this gap is being reduced, then for very small gap, what we will find F1 is equal to P c into A n. What is A n? A n is the simply this area, not the curtain area. Okay. It is observed that with the increase in x f 0 x f minus x f, that is that gap, the force F 1 increases due to the jet force and may become as large as twice P c into A n. Now, look into this. Normally, if the gap is small, this force is P c into A n, whereas if this gap is increased, this force become double. So, or in other words, I would say this we are equating here, but in other words I would say this flapper valve are designed in such a way, you will find that with small gap F 1 is equal to this, and with the maximum displacement of or the maximum with the maximum gap, with the maximum increase in this force become double, or in other words within this range we design the torque motor. Okay. So, torque motor is selected in such a way that there will be twice the torque from the minimum torque required to operate this valve. However, in practice that x f 0 by d n, d n is the diameter here, is usually 1 by 16. So, suppose if d n is equal to say what I would say 1.6 millimeter diameter of the or this nozzle is 1.6 millimeter. In that case x f 0 is only 0.1 millimeter, 0.1 millimeter. 0.1 millimeter you can imagine is very small. So, and again we are giving the motion of that. So, this motion is very small and very precision, and F 1 remains close to P c into A n. Differentiating equation 19 at a null point, we get this expression d f 1 by d x 0 is this much. Then this is equivalent to the spring coefficient of a fluid spring. Okay. If you compare this, we can, if we consider the mechanical spring, this is as if a fluid spring with this much of stiffness, but it is a negative spring. What does it mean? What is negative spring? So, it's normally with the increase in when this is the gradually when it is being compressed mechanical spring, the load is increasing. Here it is opposite. This cause a destabilization. Okay. Due to this negative nature, a destabilization is observed. However, the effect is small and flapper drive is made sufficiently robust to handle this situation. This means that while we are designing this torque motor, we have to consider this part and it should be robust, so that it can handle such destabilization. For balancing, providing a small piston or spring on the opposite side is common. Sometimes a spring is used in the opposite side, that is for the flapper nozzle. What happens to if if there is double nozzle? In that case, you will usually find springs are used here in both directions. Okay. In case of single nozzle, you can use this spring directly opposite, otherwise you can use also a coil spring for both directions. In double jet 4-way flapper valve, balancing is done by opposite jet. In this means that in case of opposite jet, if there is another nozzle in the opposite direction, sometimes we do not need any spring at all, because this can be balanced by the opposite one. Okay. Now, we shall continue our lecture in the, we shall discuss more about this flapper nozzle valve in the next lecture. For this lecture, the mostly I have taken from this Merritt's book, which is hydraulic control systems. Also, particularly to know about the drift, this paper is important. So, you can go through this paper, and there are some general idea from the Blackburn book of Blackburn and Rayford and Scherer. Thank you for listening.